Welcome back. In this video, we are going to solve problem 14-15 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the bending strain energy stored in the simply supported beam subjected to uniformly distributed load. EI is constant. So you can see this is a simply supported beam having pin support at this point and a roller support at this point. And there is a uniformly distributed load over a length of L by 2 from this pin support. So we have been asked to determine the bending strain energy stored in the beam. So let's start with the solution. So as we know that bending strain energy is equal to integral of m square dx over 2ei, and that will be from 0 to length. Limit will be from 0 to L. Now what we will do is that you can see if this is a point A and this is point B, and if you remove this pin support at point A, so you will be having a reaction force which is equal to RA, and if you remove this support at point B, so you will be having a reaction force which will be equal to RB. So first we will find this RA and RB by using equation of equilibrium, and when this distributed load is converted into a point load, it will act at the middle, and this load will be equal to W into over length which it act, and it is WL. It will be L by 2, and it will be acting at half of L by 2, which is equal to L by 4. So this is L by 4, and this will be also L by 4. Now you can apply equation of equilibrium. So what will be the first equation of equilibrium? The first equation of equilibrium will be sum of all moments about point A is equal to 0, taking the counterclockwise moment as positive. So about point A, first moment will be this load which is WL by 2, and that will act perpendicular distance is L by 4, and this is producing clockwise moment, so it will be negative. So I will write minus W into L by 2, and perpendicular distance is L by 4. The second moment about point A is due to this RB load, and the perpendicular distance is L, and this is producing counterclockwise moment, so it will be positive. So I will write plus RB times L is equal to 0. So from here you will get this RB into L will be equal to WL square over 8, and this RB will be equal to WL by 8. So this is reaction force by the roller support on the beam. Now we'll find this RA by using equation of equilibrium, that sum of all moments about point B is equal to 0, and taking the counterclockwise moment as positive. So about point B, the first moment will be this WL by 2, and perpendicular distance will be this one. So L by 2 plus L by 4 will give you 3L by 4. And this is producing counterclockwise movement, so it will be positive. So I will write W into L by 2, and perpendicular distance is 3 by 4 times L. The second moment is produced due to RA, and perpendicular distance is L, and this is producing clockwise movement, so it will be negative. So I will write minus RA into L is equal to 0. So from here you will get RA into L will be equal to WL square 3WL square over 8. So from here you will get RA will be equal to 3 times WL by 8. So this is the reaction offered by this pin support on this simply supported beam. Now what we will do is that we will find internal movement. So for that I will cut the beam over any length of L by 2, and we will take this distance is x1, and we will draw the free body diagram. So I will write internal movements for coordinate x1. So I will draw the free body diagram. So let this is the beam. Clear, you have RA which is upward, and this RA is 3WL by 8. This distance is X1. Clear, and there is a uniformly distributed load acting over a length of X1. This is W. And when you cut it, you will be having a shear force V1 and you will be having a moment M1. Let this is your point 1. Now what we will do is that if you convert this W into point load, so it will be W into the length over which it acts, which is X1, and that will be acting at a half of X1. So this will be X1 by 2 and this will be also X1 by 2. Now we'll find this moment by using equation of equilibrium. So what will be that equation? That sum of all force moments about point 1 is equal to 0 and taking the counterclockwise moment as positive. So about this point, the first moment will be this W into X1 and perpendicular distance is X1 by 2 and this is producing counterclockwise moment, so it will be positive. So I will write W into X1 and perpendicular distance is X1 by 2. The second moment is due to this load and perpendicular distance is X1 and this is producing clockwise moment, so it will be negative. So I will write minus 3WL by 8 into X1. And the last moment is, you can see, external moment M1 or reaction moment, which is counterclockwise, and that is positive, and the sum of all moment is equal to 0. So from here this M1 will be equal to 3WL over 8 X1 minus WX1 square over 2. Clear? So this is the internal moment for coordinate X1. Now what we will do is that we will find internal moment for coordinate X2. And what will be X2? So if you cut the beam over here any length of X by L by 2, so let this will be X2, and if we draw the free body diagram, it will be like this. So you can see here this is point B where RB and RB is WL by 8. Clear? And this is the distance which was X2 coordinate. Clear? So when you cut it, you will be having a shear force V2 and you will be having a moment in clockwise M2. So we will find this M2 by using equation of equilibrium, that sum of all moments about, let this is point O is equal to 0 and taking the counterclockwise moment as positive. So about this point O, the first moment will be due to this load WL by 8 and perpendicular distance is X2 and this is producing counterclockwise moment, so it will be positive. So I will write WL by 8 into perpendicular distance is X2 plus there is external moment M2 which is clockwise is, and the sum of these moments will be equal to 0. So M2 will be equal to WL X2 over 8. So this is the internal movement due to coordinate X2. Now we have both these movements, so we will use this formula in order to find the bending strain energy stored in this beam. Okay, so what we will do is that we know that bending strain energy, let me write it, bending strain energy which is equal to Ui is equal to integral of 0 to L m square dx divided by 2EI. If we take EI as common from, because we have two coordinates, so 2EI will be outside and we will left with integral of m squared dx1 over 2EI, and the limit will be from 0 to L by 2 for x1 plus integral of 0 to L by 2 and moment will be m2 square dx2 over, okay, so 2EI is already taken outside, so no need to repeat it. Okay, and this will be M1. Now you can just put the value of M1 and M2, which we have. M1 is this one and M2 is this one. So you can just put it, Ui is equal to 1 over 2 times Ei into integral of 0 to L by 2, and M1 is 3 omega WL over 8 x1 minus Wx1 square over 2 whole square into dx1 plus integral of 0 to L by 2, and M2 is WL x2 over 8 whole square into dx2. Now if you apply the formula a minus b whole square, so it will be equal to 1 over 2 Ei integral of 0 to L by 2. This will be equal to 9 W square L square x1 square over 64, clear, plus W square x1 4 over 4 minus 2 times this multiplied by this will give you minus 3 W square L over 8 x1 cube into dx1 plus this will give you integral of 0 to L by 2 W square L square x2 square over 64 dx2, clear. Now if you further expand it, it will be equal to 1 over 2 times E1, and that will be integral of 0 to L by 2 9 W square. Okay, so you can just skip this step. You can directly take the integral of x1 square into dx1. So it will be equal to 9 W square L square over 64 multiplied by x1 cube over 3, and limit will be from 0 to L by 2. Similarly, it will be equal to W square x1 power 5 divided by 4 multiplied 5 will be 20 minus 3, and the limit will be 0 to L by 2. Similarly, minus 3 W square L over 8 into x1 power 4 over 4, and limit will be from 0 to L by 2, plus this will be equal to W square L square x2 cube over 64 multiplied by 3, and limit will be again 0 to L by 2. Okay, if you simplify all these and put the limits, replace x1 with L by 2 here, similarly here, and x2 with L by 2. You can do it, it's very easy. So you will get 1 over 2 Ei into, okay, so you will, if you all simplify it, so you will get the final value will be equal to 17 W square L5 over 15360 Ei. So this is the amount of strain energy that is stored due to bending, or it is also known as bending strain energy. And that was all about this problem 14-515. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing further. Thank you for watching. Welcome back. In this video, we are going to solve problem 14-18 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the bending strain energy stored in the simply supported beam subjected to triangular distributed load. EI is constant. So you can see this is a simply supported beam having a triangular distributed loaded the magnitude here is W naught, and here the magnitude is 0. So you have to find the bending strain energy stored in the beam. So let's start with the solution. So as we know that bending strain energy UI is equal to m square dx divided by 2EI, and there is an integral from 0 to whole length L. Now we will find this moment M. So what we will do is that first step is that if you remove this pin support at this point, so you will be having reaction force. Let this point is point A. So this reaction force will be AY, and there is a roller support at this point B. And if you remove this roller support, so there will be reaction force which will be equal to BY. So first we will find this AY and BY by using equation of equilibrium. Now you can see that this is a triangular distributed load. So when it is converted into a point load, so it will be, the magnitude will be equal to 1 over 2 W naught and the length over which it acts. So it will be this one. And that will act at a distance of L by 3 from B side. L by 3. And this distance will be 2L by 3. 2L over 3. Now we'll find this AY and BY by using equation of equilibrium. So first equation of equilibrium is that sum of all movement about point B is equal to 0, and taking the counterclockwise movement as positive. So about point B, the first movement will be due to this load 1 over 2 W naught into L, and the perpendicular distance is L by 3, and this is producing counterclockwise movement, so it will be positive. So I will write 1 over 2 W naught into L, and perpendicular distance is L by 3. The second movement that is produced due to this AY and perpendicular distance is L about point B, and this is producing clockwise movement, so it will be negative. So I will write minus AY into L, and their sum must be equal to 0. So from here we will get AY into L is equal to W naught L over L square over 6. So from here you will get AY will be equal to W naught L by 6. So this is the reaction force that this pin support applied on this beam. Now we'll find this BY by using another equation of equilibrium, that is sum of all forces along Y direction must be equal to 0, and upward force is taken as positive. So AY, which is upward, so W naught L over 6 minus this distributed load, triangular distributed load when converted into point load. So 1 over 2 W naught L plus BY is equal to 0. So if you take the LCM, that will give you 6. 6 divided by 6 is 1, and 1 multiplied by W naught into L will be this one. Similarly, 6 divided by 2 is 3. So 3 into minus 1 is minus 3 W naught into L plus BY is equal to 0. So from here you can see this BY will be equal to 2 W naught L over 6, or if you further simplify it will be W naught L over 3. So this is the value of BY. Now we have this AY and BY. So what we will do is that we will find moment. So we will cut this beam at any length X. For example, if we cut the beam over this length, let this length from this point A is X. Clear? And draw the free body diagram. So let me draw it over here. That this is the beam. Clear? This is point A where you have AY, and that AY was W naught L over 6. This is the length X where you cut the beam, and when you cut the beam you will be having a shear force that will be acting thisward V, and you will be having a moment M as well. And you can see you have a triangular load as well at this point. Now you can see W naught is the magnitude at this end. So what will be the magnitude at this? So let W is magnitude over here. Now you can see you have two triangles, similar triangle. One is this larger one, and the second one is this smaller one. So by using this ratio, W naught over L, W naught over L is equal to this W over length which over which it x is x. So from here this W will be equal to W naught x over L. So at here the magnitude is W naught x by L. Now when you convert this triangular load into a point load, so it will be equal to 1 over 2 the W naught x over L and the length over which it acts, and that is x. And it will act at a distance of x by 3 from this side. So x by 3. Okay. Now let this point is point 1. No, so we will find this moment by using equation of equilibrium that sum of all moment about point 1 is equal to 0, taking the counterclockwise moment as positive. So about point 1, the first moment is this counterclockwise moment or reaction moment which is plus m. So I will write plus m. The second moment due to this load and perpendicular distance is x by 3, and this is also producing counterclockwise moment, so it will be positive. So I will write plus 1 over 2 W naught x over L into x, and perpendicular distance is x by 3. And the last moment is due to this load into perpendicular distance is x, and this is producing clockwise movement, so it will be negative. So minus W naught L over 6 into x is equal to 0. Okay, so m plus W naught x cube over 6L minus W naught L x over 6 is equal to 0. So you can take the LCM. So this is 6L, and that will give you W naught x cube minus W naught L x is equal to 0. So this moment will become equal to minus W naught x cube plus W naught L x over 6L. And when you take this W naught common, so W naught over 6L is common. So you will get here is W minus x cube plus LX. LX. Okay, LX. Okay, this is when you divide this by 6 will be L, and that will give you square. So it is W naught L square x. So here I will have L square x. Now you can also write it, the moment equation is W naught over 6L, and that will be equal to L square x minus x cube. So this is the moment equation. Okay. Now we will use this moment equation in this equation in order to find the bending strain energy. So let's move. We know that bending strain energy is equal to integral of 0 to L m square dx divided by 2EI. So just put the value of moment over here. So moment is W naught over 6L into L square x minus x cube, and we will take the square into dx divided by 2EI. Okay, so integral of 0 to L, it will be W naught over 36L square into L square x minus x cube whole square into dx divided by 2EI. So when 2EI multiply with 36, we will take constant outside, so it will be 32L square, 72L square EI, and we will left with integral of 0 to L, L square x minus x cube whole square dx. Okay, now further simplified, so W naught, okay, this is W naught, this will be W naught square. Okay, because we are taking the square. Okay. Okay. So W naught square over 72 EI L square integral of 0 to L. Now the square of this will be equal to L4x square, clear, plus x6 minus 2 times this term into this term. So that will give you 2L square x power 4 into dx. Okay. Further simplify W naught square over 72 EI into L square into integral of this term. So integral of L4x square will be L4x cube over 3 plus integral of x power 6 is x7 divided by 7 minus 2L square x5 over 5, and limit will be from 0 to L. That will give you strain energy due to bending. So W naught square over 72 EI L square. Now if you put the limit L, so it will be L4 into L power 3 divided by 3 plus L7 over 7 minus 2L square L5 over 5. Okay. So further simplify W naught square over 72 EI L square, and that will give you L7 over 3 plus L7 over 7 minus 2 L7 over 5. That will give you strain energy due to bending. And when you solve all these, you will get at the end strain energy due to bending in the simply supported beam comes out to be W naught square L5 over 945 EI, which is the answer of this question. So this is the amount of strain energy that will be stored in this simply supported beam due to bending. And that was all about problem 14-18. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my channel with your friends and help them in learning as well as and help me in growing my channel further. If you have any question, you can ask me in comment section. Thank you for watching.